Good morning, dear friends. Today we are going to discuss one of the module in crystallography. And the concept that I am introducing today is the concept of Miller index. Popularly in the plural form we call that concept as Miller's indices. So I am writing this concept here, Miller's indices. So if I am explaining this concept Miller indices, specifically I want to correlate this concept to the nomenclature of lattice planes inside any type of a system which is a crystallographic system. So I write this as giving name, simple configuration, giving name to a plane, to a lattice plane. Let us say giving name to a lattice plane. That is what is this concept of Miller's indices. Singular form is index and the plural form becomes indices. The concept comes here, why do we index the things? What is the need? What is the necessity? So, to explain this I will tell that suppose, for example, the first nomenclature that is done in our life is the name that is being given to you by your father, by your mother. Assume for some length of time that you are not being given with any name. Then what will be happening? So, if you are not being given with some name, you lose this index. Suppose there are 60 students inside the class and all these students do not have any name. Then assume the problem with the teacher. 60 students with no names. So, the first thing that is being done by your father and mother is that they have given you an index. Now, is there any universal conclusion in giving that particular name? I don't suppose. It is just by some calculation or by some interest or by some analogy, they give you some nomenclature and that becomes your index that you carry for the lifetime. But it makes so many things easy. How does that make many things easy? Like you can be identified in a crowd. Okay, so that is the simplification of information. So first point that I am making it clear is index simplifies the information. Second thing, suppose I am dealing with this particular content of information inside the same class with 60 students and each student is having certain number of set of names with him now. Like one student is having his own name, his father's name, his surname, nowadays his mother's name also. So he is carrying at least 4 nomenclatures with him and there are 60 students inside the class. Then if 60 students and every student is having 4 nomenclatures with him, then we will be having 240 nomenclatures inside the class itself. And if a teacher tries to identify each student by all these 240 names, then this is the only thing that the teacher has to do in the entire semester. Because it is very difficult, it is very lengthy, it is very complicated. Now how do we simplify this? The simplest method being adopted by any teacher is giving you a certain index that is called as your roll number. So instead of knowing all 4 names, I just give you roll number 1 or roll number 2 up to roll number 60. So if I am giving this name, how does that make my work simple? Then I can fit all the information related to some student, say in a worksheet, by putting a roll number, then entire information related to that particular student in subsequent columns, subsequent rows. His name, his surname, where from he has done his 10th, where from he has done his 12th, and so many other things, his height, how many marks he has scored in CET, and so many things. So the entire thing as information content, which is infinitely available, is being made finite by giving this particular roll number. So coming to the conclusion, the second important thing that we achieve by giving an information is systemizing the infinite information into a finite set of variables. So making, this is first, so making infinite information finite. Finite. So we have a lot of information available, but the processing brain is finite. That is my limitation. So if my processing brain is finite, I need to systemize the things in such order that I can recognize these things and I can, work with these things. Now, this is the thing. And third thing, this is not universal. No universality should be claimed. What is the meaning? Why no universal? The meaning of being not universal is, suppose I am giving some student a roll number, say 15. No one is going to call that student as roll number 15 in the entire lifetime. Or at the age of 80, no one is going to call him roll number 15, please come here. This is just a temporary attachment for that semester or for that year. It is going to change. So there is no universality. So if I am giving some roll numbers 1 to 60, some other teacher can also change it. Say he can say that roll number 60 is roll number 1 now and roll number 1 is roll number 60 in the reverse way. Now does that change anything? It doesn't change anything. So no claim of universality should be made with any indexing pattern. So indexing is making my information simple. Indexing is making my information finite. And lastly, there is no universality. Everyone can arrange the information in his or her specific way. And there is no claim that one can make that mine method is the only correct method. So, now how do we correlate all these indices with crystallography? Upon any crystal we take, the crystal is conjugation, assimilation of so many lattice points. So there are lakhs of lattice points being arranged in a particular specific way. We call it regular way and periodic way. See, this regularity and this periodicity results in the formation of the crystal. So we have so many lattice points, and in every lattice we have so many identifying planes. Now how many types of planes we can say? There are certain planes which are called sectional planes. There are certain planes which are called lateral planes. There are certain planes which we call as coordinate planes, they are attached as x, y, y, z and zx planes. There are certain planes which we call at atomically deficient planes because atoms hardly exist in them. Certain planes are atomically rich because density calculations can be done with reference to them. So these are called dense planes. So when we go in contextuality, there are so many such types of varieties of planes that exist as lattice planes inside any structure. Now, if I want to recognize a particular system with existence of certain planes inside it, I should know where these planes exist. Then, if I recognize it by analysis, I should be able to give certain nomenclature to it. Now, there are ways in which we can give this nomenclature. I think this is understood. I remove this now. Now, how to give nomenclature to a plane? Firstly, I am going to give you an idea of giving nomenclature to a plane with simple mathematical techniques. Say for example, a particular plane is, suppose first plane, second plane and third plane. Suppose these three planes are identifying one point. Getting my point? That one plane is conjugation of three different planes crossing each other. Then suppose this is plane 1, this is plane 2 and this is plane 3. Now all these three planes will have certain equation with them. Suppose this equation I call as ax1 plus by1 plus cz1 plus d1 is equal to 0. This is plane 1 equation that I am writing here. Plane 2 equation we will write here. That ax2 plus by2 plus cz2 plus d2 is equal to 0. This is second. Third, ax3 plus by3 plus cz3 plus d3 is equal to 0. This is one way. If these planes are being defined with different points, if the point is same, the same will be a1x plus b1y plus c1z plus d1 is equal to 0. a2x plus b2y plus c3z plus c2z plus d2 is equal to 0. Then a3x plus b3y plus c3z plus d3 is equal to 0. So these three planes are identifying one point. Then I need to solve it for getting the value of x, y and z. How do we solve it? By the method of determinants. Like I will have some determinant into x, y, z is equal to some values, say constant values. So ax is equal to b format. And then I find the inverse to get the values of x1, y1 and z1. Now what does this signify? I get 1 point. Now how many such points I need to identify one plane? At least 3 points. 2 points identify a line, 3 points identify a plane. So naturally I have to solve in this mathematical way 3 times to get 3 exact nomenclatures of 3 different points which can give the definition of one plane. 3 points identify a plane. So I need to solve this long method for 3 times to get nomenclature of one lattice plane inside the crystallographic system. Don't we find this method to be a very long method? Definitely, it is a very long method. So we need to have certain method which is a short method, which does not involve all such mathematics related to the calculation part of it, because then every time I will need some software to solve this, and I need to find correct nomenclature without involving a lot of mathematics associated with it. So many methods were described, and out of that the simplest method, I can say, simplest of all these methods being adopted across the entire range of crystallographic community, I can say, is the method which is called as Miller's method. So Miller's method is the simplest method. Why we call this method to be a simplest method? There is one line being written in the book of Azraf. Dr. Azraf's book is there, which says that it identifies a plane without involving mathematics. It is just like coming to your home without knowing your address. So if I can do it with any one student and I can reach to the address of the student without knowing his real address, I reach his home, then you can say that by some way I have done it. But if it is true for all 60 students, then you must say that I have a method. So This Miller's method does not involve much of analytic calculations. It does not involve a lot of mathematics, and rationally it gives you the nomenclature of any crystallographic plane. So now I am giving you the definition of a Miller index. What is a Miller index? What is a Miller index? The definition says reciprocal of characteristic intercepts. So I am giving you just a working definition. Classically, a long definition can be given. I am just giving you a working definition. That is reciprocal of the characteristic intercepts with no common factor. So you involve certain reciprocals of characteristic intercepts. Now the question is, why reciprocals? The answer has to be very simple. In fact, the answer is, it is Miller's method. It is not my method. So if it is Miller's method, I need to follow what Miller has said. But there is a rationality. There is certain logic that works behind this. And the logic is, I can have an index, say 2, 2, 2, 3, 3, 3, and so on. I can grow on with that index. So as the index grows, the distance is growing if I don't take the reciprocal. But if I take the reciprocal, 2 is more, but 1 by 2 is less. 3 is more, but 1 by 3 is less. So what is the intention in taking the reciprocal? Is that as we grow away from the origin, the distances grows, but the index reduces. The index is more, and index, suppose this distance is there, as I am growing with the distance is more, but the index is less, and the distance is less, the index is more. So this is a reciprocal approach. I want to be very rational and very logical while I find the index. So reciprocal of characteristic intercepts. Now what is the meaning of no common factor? It does mean that I cannot take any direction assumed. I cannot assume that a plane is only 1, 1. With all threes are 1. Only saying it 1 times 1 will not suffice, because the first one indicates the growth in the direction of x-axis, the second indicates the growth in the direction of y-axis, and the third will indicate the growth in the direction of z-axis. So in together 1, 1, 1 is growth in the direction of x plus y plus z-axis, and that suffices the primary definition of lattice translational vector. And lattice translational vector is sufficed, you have defined a plane. Okay, so to define a plane, it must be a volume plane and it cannot be a surface plane. Please keep this in mind. Miller is not talking about any surface idea. Miller is talking about volume planes, lattice planes, which are defined primarily and compulsorily by the presence of x coordinate, y coordinate and z coordinate inside it. So that is the meaning of no common factor, and even if the growth in two directions are similar and same, at least the direction is different. So that's where it has to be taken separately. So reciprocal of characteristic intercepts with no common factor, I can say, is one rational definition, one rational approach that we can say is the definition of Miller index. Now, what are the steps involved in defining this particular Miller plane? Now the first step, find the characteristic intercept form. Find the characteristic intercept form. Suppose for example, I draw here one cube, and in the cube I am showing one say for example, any plane, let us say this plane I am defining here. This is my origin, this is the direction of x-axis, this is the direction of y-axis, this is the direction of z-axis. So all three axes are defined. This is the plane. Then for this plane I need to find the characteristic intercept form. Where does it cut? To x-axis. It cuts to the x-axis at point A. Where does it cut to the y-axis? It cuts to the y-axis at point B. Where does it cut to the z-axis? Again, it cuts at a distance, say C. If it is a cube, all these distances will be same. So in that sense, A is equal to B is equal to C is equal to A, then every such distance will be equal to A only. Now what will be my characteristic intercept form? My characteristic intercept form will be A, comma A, comma A. You can give a round bracket, also the commas. Now this is the characteristic intercept form. Second step is finding the reciprocal form. So whatever step 1 gives me as intercept form, I need to take the reciprocal form of it. So if I have got A, my reciprocal form says 1 by A. Again A, it is 1 by A. Last A, 1 by A. So I have 3 1 by A, 1 by A, 1 by A. This is my reciprocal form. In the third step, we need to find the least common factor, okay, or least common multiple factor. This is LCM. Now these are the three figures with me, 1 by A, 1 by A, 1 by A. What will be the LCM? Of course, A will be my LCM. Then the fourth step is Miller index. We call it as round bracket HKL, round bracket HKL. Then it will be this Miller index HKL will be equal to this LCM into reciprocal form. Again I repeat, my Miller index is nothing but LCM into the reciprocal form. Okay, what is my LCM? It is A. What is the reciprocal form? 1 by A, 1 by A, 1 by A. So it will be 1, 1, 1. Now don't give commas here. If you give commas, then it is not called Miller index. So it is 1, 1, 1. This is the definition of the Miller index. So this is first thing. Now if I take, just extending the idea further, for the same point, we will be talking about the rationalization of the same concept with the planes which are intercepting in the negative directions. So this is for the first lecture. I am stopping here. In the coming lecture I will be talking about the Miller's indices and finding these Miller's indices if the directions are negative x, negative y, negative z directions, and if a certain plane does not cut to a certain direction, then what will be the status of the index associated with it. So this is the point of my focus in the coming lecture. Thank you. Thanks a lot.